Thank you, Adam, for this introduction. And just to make one thing clear, I'm not such a fan of Bitcoin, but I am of the blockchain technology behind it. And blockchain technology that we look at as ING does not use proof of work, so we don't have the computational and CO2 waste, fortunately. All right, I will explain you how you can preserve privacy on a blockchain. I'll also go into why that's a difficult thing to do in the first place, and then we'll have a look at that. But first, I have a question to you. Who of you checked in code last week? Okay, the majority, that's good. And then that also applies for commit and push. When I say check in, I use them interchangeably. All right. So let me start with a little story. Last year, I bought a new house. And as many of you know, what you do is you obviously first agree on a price with the seller of that house, and then you agree on the terms, when you will get the keys handed over and the ownership handed over. And you need to do either a down payment, or you need a guarantee of your bank, a statement that you're good for at least 10% of the value of the house, in case you change your mind and you don't want it at all. And to make this agreement work, to make it enforceable, you go to a notary, he drafts a piece of paper, and you need to sign it manually with a pen. So, as I'm sitting there at this the notary, it's a very fancy office, marble floors, and old guy in a grey suit, and I'm holding this piece of paper and a pen, and I'm about to set a wet signature on this piece of paper. I say to myself, why? Why am I here signing a piece of paper? Mind you, that was 2017, and since 2008, there's blockchain. In 2008, the Bitcoin paper was released, and the big novelty, besides the cryptocurrency, the big novelty of the technology behind it was that there's trust in the network, that you spend your Bitcoin only once, there's no double spend. If I would possess 3 Bitcoins and I would pay 1 to my colleague Arturo, then I would after that possess only 2. And the whole network can verify that, and there's no trusted third party there. 2008, the paper was released. Then 2009, Bitcoin went into production. In 2010, the first payment was done with Bitcoin. So 2 pizzas were bought for 10,000 Bitcoins. I hope the pizza delivery guy kept his Bitcoins, he held on to them. He would be very rich today. More importantly, while Bitcoin is restricted, Bitcoin technology is restricted to doing payments with cryptocurrencies. A couple of years later, in 2013, Ethereum went live. And what Ethereum does, it adds a Turing-complete virtual machine to the blockchain, which works similar to Bitcoin. And what that means is, with that Turing-complete virtual machine, you can build any logic you want. And so any application that requires and benefits from trust between untrusted parties and decentralization can be built with Ethereum. And so, for instance, if you you buy a house and you want the ownership to swap atomically with the payment, one transaction, either it both happen or none of them, then you can build that with Ethereum. You can do that today, which is why I was so surprised that last year, 9 years after the invention of blockchain, we still use paper and a pen and trusted third party. I mean, this trusted third party, the notary, if you go there, you pay €1,000 for his services. just to make sure that the contract is right and the clauses in it get executed. Which is why, for instance, if you have a smaller payment, like you buy a car, you just hope for the best. You do a down payment to the dealership. You hope he doesn't go bankrupt in the meantime. Sometimes they do. You hope they don't run away with your money. I mean, even notaries, sometimes they run away with your money. I read in the Telegraaf, so that might be fake news, but which is why it's a huge improvement if you can do that on a blockchain. It's cheaper, and the trust is decentralized by the tens of thousands of computers reaching consensus on the validity of the transactions. So on Ethereum, if you look at this website, State of the dApps it's called, dApps for decentralized applications, you see many applications, over 1,000, but they're all quite small. Apart from crypto kittens, and nothing very serious is, very mainstream is going on Ethereum yet. You also see large companies, financial industry, but also many other industries, looking at blockchain technology, doing proof of concepts, pilots, even live trades. Like ING earlier this year, we did a trade on a securities trading platform, which was legally binding. So also that part is solved. However, even that application is not yet in full production. Why is that? With the technology being around for 9 years, or Ethereum for 5 years, why do we only see things like crypto kittens or other small niche applications, but not yet any mainstream application on blockchain technology? It's basically because of two things: privacy and scalability. Scalability I will not address in this talk. If you have any questions about that, we can do it in the Q&A after, or in the break after this talk. I will be at the stand, the ING booth, so you can visit us there as well. But privacy I will address in this talk. Why is privacy an issue on a blockchain? I mean, if you look at traditional or centralized systems, where a company runs and controls a database with customer data, then you just put some firewalls around it, and there's no technical reason. If you have your security policies well implemented and it's, your security is in order, there's no reason why information should leak. Unless it's your business model to leak information. We've seen examples of those as well. But so with traditional centralized systems, it's easy. But with a decentralized system, like blockchain or distributed ledger technology, as it's also called, you need consensus between a large group of validators. And these validators are typically different parties. In the case of Bitcoin and Ethereum, tens of thousands of parties that control computers that validate transactions, and they need to reach consensus. And if you have all these parties validating transactions, that means they must see the transactions, right? Otherwise they can't say, is this a double spend or not? And so in order to have everyone validate all the transactions, you automatically leak information. If I do a payment to my colleague Arturo, and they do it on Bitcoin, then the whole world would see the payment going from a public address, Bitcoin address, my address, to another public address, and everybody would see the amount. It's difficult, but not impossible, to determine the identity behind our addresses. Typically that's done through the exchanges, where you exchange from traditional money, euros, dollars, etc., to Bitcoin and vice versa. So that's a problem. How can it be solved? There's several solutions. There are ways mechanisms in which not every participant in the network needs to receive all transactions. Example of that are channels, as used in Hyperledger Fabric, private transactions, things like state channels or payment channels. You probably have heard of the Lightning Network built on top of Bitcoin. Basically what it does is you lock up some of your funds, like I lock up 10 Bitcoins, and say I do a lot of transactions with my colleague Artur. He also locks up 10 Bitcoins, and we can do peer-to-peer transactions outside the blockchain. And all these individual transactions remain undiscoverable. They are digitally signed, so in case we disagree what would be our mutual balance, then we can replay all the transactions on the blockchain, but typically you don't have to. So it's very good for scalability, that's where it originates from, but also because you hide individual transactions from the blockchain, it also helps with the privacy. Intel SGX, it's a hardware solution where you can send encrypted data to somebody else, somebody who runs an SGX machine. The SGX machine has a built-in private key to decrypt that data and to validate it. And while it's decrypting and validating, it does so in a reserved memory space where no other process can access it. And in that way, you can have validations done by multiple parties. And even though the computers they run validate the transactions, the owners of those machines, the operators, don't see the plain texts of these transactions because it's secure hardware. And there are various cryptographic solutions. For instance, homomorphic encryption. Homomorphic encryption means that you can encrypt data but still do calculations on it. Like for instance, if I encrypt the numbers 3 and 5 using RSA, and I multiply the ciphertexts and then decrypt it and take the modulo, then I end up with the number 15. So you can still do some validations on the ciphertexts because ciphertext, they, depending on the cryptographic scheme, they preserve some homomorphic properties. Some allow for additions and others for multiplications. Ring signatures. A ring signature basically means it's a digital signature where you know that it's signed by one of a group of public keys, but you don't know which one. So you can hide identity there while still having valid signatures. And zero knowledge proofs, where you provide a proof that can be validated, but nothing else besides that proof is revealed. We'll have a look at that at an example of that later on. So I just said, if you want to reach consensus on a blockchain or distributed ledger, you must share transactions with the whole network. In order for everybody to validate and reach consensus on it. Well, what happens if you don't? Let's have a look at a quorum. It's a DLT. It's a blockchain based on Ethereum, but with two modifications. They took out proof of work to make it usable for permissioned networks. So networks between companies. Instead of everyone in the world running nodes, you can now have a network of companies running it. And because they took out proof of work, they made it much more energy efficient and also much higher performance. And also they added private transactions. And what it does is, you see here 3 nodes, party A, B, and C. So these vertical blocks, they are nodes. And they're connected in 2 ways. And through a regular Ethereum network, that's what you see here on the left. And through what they call the constellation network, what you see on the right, it's a peer-to-peer network. And you see that every node has 2 states, a public state and a private state. And what it basically means is you can send public transactions like in Ethereum, and they update your public state, and you reach consensus on that. And that's the thing that remained, that remained unchanged. But what they added was this new network they call Constellation, where you can send encrypted transactions peer-to-peer. And you encrypt it with the public key of the recipient. So, for instance, if party B does a transaction with party C, and if party A does a transaction with party B, and party C is not allowed to see it, party A will encrypt the transaction with the public key of party B, send it peer-to-peer through this green constellation network. Party B will receive it, party C will not. And party A will store a hash of the transaction on the public blockchain, on the Ethereum blockchain. So party C and B will see the hash, which is stored on the blockchain. Party B and C will both see, did I receive a transaction which matches this cryptographic hash? Only party B does so. So party B will update its private state, and party C will not. And because party C does not even receive the encrypted data, this is a pretty strong way to preserve privacy. It does come with a side effect. Let's look at this smart contract. We just did the raise hands of you checking in code, quite many of you. So even though this is Solidity, which is not programmed by so many people, I think this is fairly readable. It's a smart contract that can run on Ethereum. It has a global state called counter, starting at 0, and every time you invoke the increment function, the global state will be updated. So what happens if you send transactions not to the whole network but to parts of the network? Let's see. I made this table. In the first transaction, private for all nodes, all 7 nodes in the network receive it, then everybody ends up at 1. I invoke the increment function for all the nodes in the network. Then on the second line, you see I send a transaction to nodes 1 and 2. They increment their state, the others don't. I do that on and on and on until transaction 7, which is public and doesn't work with a private transaction, so it doesn't, public transactions don't work with a private contract, so it doesn't update. But what you see is that after sending a couple of transactions to parts of the network, that all the nodes in the network, they have different states, and more importantly, they don't know each other's states. So even though this partial transaction sharing is strong in preserving privacy, you lose your consensus, which was the first reason why you started with blockchain in the first place. And so you need to basically reintroduce the reconciliation, which we want to get rid of by using blockchain. And it's so this was the first MVP of Quorum. It was a bit naive approach, if I may call it that. I must also say that they are working since they went live with this last year. They're also working on adding more advanced privacy features. So how can you do partial transaction sharing? Well, let's look at how Corda does it. Corda uses the unspent transaction output model, or UTXO, which originates from Bitcoin. And what you see here is 2 Bitcoin transactions. I'll first explain how it works in Bitcoin, and then I'll explain how that relates to Corda. You see that transaction 1 starts with an input, 50 Bitcoin. Many years ago, the mining reward used to be 50 Bitcoins, and now it's 12.5. It halves every 4 years. I think in 2 years from now, it will go to 6.25. But you see that transaction 1, it uses the input, mining rewards of 50 Bitcoin, and 2 outputs. One of half a Bitcoin, and one of 49.5. So you see that the sum of the inputs and the sum of the outputs, they need to be equal. That's a validation rule of Bitcoin. Then you see transaction 2. It uses 3 inputs. the half a Bitcoin received in transaction 1, 0.8 and 0.3 received in other transactions, and it produces two different outputs. And so basically what you see is in transaction 1, somebody pays half a Bitcoin to somebody else and keeps the 49.5 for himself. And in transaction 2, somebody pays 0.8 Bitcoin to somebody else, and he keeps 0.8 for himself. And again, with transaction 2, you see that the sum of the inputs equals the sum of the outputs. And the nice thing here is that when you do a transaction 2, you can go back because you refer to previous transactions. In Bitcoin, not only the blocks refer to previous blocks, but also the transactions, the inputs refer to outputs of previous transactions. And that model is also used by Corda, with two differences. Where Bitcoin shares all the transactions with the whole world, global broadcast, Corda only shares it with those parties involved in that transaction. That's one difference. And the reason they do it is so that everybody sees, can verify the history of that transaction from its issuance until the current transaction. The other difference is that Bitcoin only does this for payments, Bitcoin payments, and in Corda you can model any state transfer, whether it's identity management or trade finance, or payments or cash on ledger or whatever, you can model with UTXO model. How does it look in Corda? Here we see 3 transactions. And you see there are 3 different types of assets on this ledger: cash, bonds, and IOUs. And what you see in the last transaction, the big box, is that in order to validate the cash payment done by Alice to Bob, and the pay A arrow, you see the 10 British pounds, 10 GBP being transferred from Alice to Bob. In order to verify that Alice is indeed the owner of these 10 pounds represented on the ledger, you go back the history of the chain, of the transactions. And so you go back to this transaction, where you see, you check that indeed the payment was done, in this case from Dan to Alice. It was signed by Dan, so these green checks, they indicate the verifications that you do. And then you also go back to that the actual cash was issued by Charlie, signature C, you see here on the left bottom, and it was issued to Dan. Where you, in Bitcoin, the issuance is always the mining reward, coin-based transaction. And so whoever wins the proof of work puzzle, he gets 12.5 Bitcoins, which is issued every 10 minutes. On a DLT like this, you can model it however you like. So for instance, how this would work with cash on the ledger is that you pay 10 British pounds to Charlie, and then in return for that, he will issue you a token that represents the 10 pounds. So unlike quorum, where you have, when you do selective multicast, where you only share transactions between part of the network, but where you could do a double spend because you don't know whether somebody is a rightful owner. Here in Corda, you have the history of the assets from their issuance until the current transaction. So that you can validate. And there's one more thing needed to prevent double spend, which is the Corda notary. In Corda, there's a notary service, which is the a consensus service, which is abstracted away from the business logic, but it's a service that takes care of the uniqueness, timestamping, ordering of the transactions. It can do so by just the cryptographic hash, and optionally you can choose for it to validate the business logic, but then it should receive the transactions. So if you want to do it in a private way, then it will take care of the uniqueness, timestamping, and ordering. So you won't have double spend. But if you want to be more robust, you also send the transaction, and then it can validate also the business logic. The notary, that's not a centralized validator. It's, it has pluggable consensus. You can configure whatever you want. So, for instance, Raft-based consensus, which is crash failure tolerant. So then the notary cluster would have to be run by one organization. If one node goes down, the whole service still remains. The node can come up again. Or a BFT Smart, which is Byzantine fault tolerant, which means the notary cluster can be run by different parties, different companies or entities, which don't necessarily need to trust each other, but the consensus protocol takes care that that the validators behave honestly, that only honest transactions end up on the network. Just as proof of work does that here through the leader election and the identification if somebody votes for illegal transactions. It's built in the algorithm that it's Byzantine fault tolerant. Needless to say, the notaries should be distributed. It doesn't really make sense if you have all the consensus done by one party. Then why use a DLT in the first place? So if we go back, and we saw that quorum, it works well for privacy, but you lose your consensus. In Corda, they say we have the full transaction history combined with the notary service, and therefore you do have your consensus. However, you share your transaction history from its issuance to the current transaction. And that's, in many cases, not desirable. If I do a payment to my colleague Arturo, as an example, then he doesn't need to know where I got my assets from. So there's one solution. That's Intel Security Guard Extensions, or SGX as it's called. It's a hardware solution where the hardware creates a trusted enclave where the verification takes place. And so you send encrypted transactions to everyone in the network, and they're decrypted by the private key, which is printed in the hardware. It's built in. Then the enclave signs the response, whether it's a valid transaction or not, and it also signs over the hash of the executed code. So you are sure that somebody does not have a changed, unvalidated, is running unvalidated code in the enclave. And the nice thing is here that it preserves privacy, because you can send encrypted data to someone. You know he can validate it, but you know he can never access it, because the owner of the SGX machine does not know its private key. As a nice side effect, it doesn't only solve privacy, but it also helps to make faster consensus algorithms. For instance, proof of elapsed time, where you get a random time assigned and you need to wait for it. And then the first one, after you have waited for it, you can propose a block, and then the first one who proposes that block, he is the leader. Everybody else will validate that block, and that will be the first, the next block on the chain, as long as it's valid. And that can only work with a trusted environment, a trusted execution environment. Because otherwise, how do you know that you don't cheat and just pick a very low number and you get to propose all the blocks? So it also works like that. The concerns about these solutions are obviously vendor lock-in. This only works with Intel. Intel will manage your keys. You might have your opinions about that. Apart from that, it's conceptually a strong idea. You probably remember this. Earlier this year, Intel, the publication went out that Intel was vulnerable for Spectre and Meltdown to side channel attacks. And basically it means that one process can access the memory of another process under certain conditions. At first when I read this, I thought, well, SGX was designed to be safe. This enclave is even an encrypted piece of memory, so it's probably not an issue. But 3 days later, I woke up and I found this on, on GitHub. So actually code appeared on GitHub that exploited SGX with the Spectre vulnerability. So in all fairness, I should say that Intel provided a patch a couple of days afterwards, basically to disable speculative branch execution. So they were no longer vulnerable, and this code no longer worked there. However, yeah, I think you can conclude here that it's a race between the researchers of Intel and the rest of the world trying to find vulnerabilities, and it's not a bulletproof technology such as, for instance, RSA encryption. It's yeah, still a bit cutting edge. Well, then so far we looked at Intel, so the hardware solutions, and partial sharing of your data and the effects of that. There's also another category of solutions to provide privacy on the blockchain. The cryptographic solutions. For instance, zero-knowledge range proof. And this one comes from when we were working on an identity management solution on a blockchain, where a self-sovereign identity, the end user can decide who gets to see which attributes of his identity. And as I was explaining this solution to my mom, she said, "Cees, are you sure you want to run this on Ethereum? It's never going to work." I said, "Why, Mom? Ethereum runs this Turing-complete virtual machine. I can build anything I want on it." She said, "Cees, you make one mistake. I don't want the whole world to know how old I am." So I think she had a fair point there, which is why we sat down with the cryptographers in our team, and they come up with an existing zero-knowledge range proof protocol, which allows end users to create a cryptographic proof that a secret number lies in a known range. So for instance, you can generate a proof that your age is between 18 and some arbitrary high number, like 500, and then the whole network can validate that the proof is correct. You do need a trusted party here to provide the commitment, because your age, it's not some truth which lives on the ledger. You have to manage and administrate it outside the ledger. So for instance, your employer or your government can provide a cryptographic commitment on your age. The end user will generate the range proof, and then the whole Ethereum network can validate that proof. And while they validate that this secret number lies in this known range, and they validate the signature of the provider of the commitment, while they do that, the actual number, the age, remains secret. Obviously, this works for any range proof, so not just age proof, but also, for instance, proof of a salary bandwidth. You need to rent an apartment, but there's a minimum requirement for your salary, or proof of location, basically two numbers, two ranges, or for instance, that a payment is within limits. How we built it is basically we built a generator of the cryptographic commitment in Java. And here you see these three actors again. So the trusted party that provides the commitment, the end user, and the Ethereum network. We built a Java library to generate the commitment, a Java library to generate the proof, and you can interact with that through Web3j with a regular Solidity smart contract. That Solidity smart contract, that Solidity has built-in functions. We added a built-in function to the compiler, which takes you to our function, a verified range proof that takes a range proof and the range, and then returns true or false whether the proof is true or false. We did this. We did this in Go as an extension of the Go Ethereum client, Geth, because code in the EVM runs quite slow. So that's why we made a native precompiled contract in Go for this. And as soon as we made this open source last year, November, we got a lot of feedback from the community, including from Ethereum founder Vitalik Buterin, and also researchers from MIT responded to our solution. And the feedback basically concluded that the protocol that we chose, it was written by an external cryptographer. It was not, it was flawed. So what we did afterwards is we did research on other protocols, including bulletproofs and also many others. They all have their own pros and cons. And we rewrote the algorithm. And also the other thing we did was that the initial implementation was in Go. And though that's fast, it's also not portable. A Solidity contract you can just deploy on any running Ethereum network. But the Go code, it does mean that it only works on a network where every Ethereum client runs the ING-specific Ethereum client. It's open source, but everybody needs to install that particular client. And Vitalik also had some good suggestions how we could rewrite that in Go, because basically the reason it was slow because of one mathematical function, mod_x, modulo exponent, which, yeah, if you implement that in Solidity, it becomes really slow, but that's a very small built-in function, also in Ethereum. So we rewrote our implementation in Solidity to use that, and also we chose a different protocol. If you look at other cryptographic solutions, for instance by Monero and Zcash, Zcash also uses zero-knowledge proofs, Zk snarks. Zk snarks are generic. You can prove and verify any statement, where our zero-knowledge proof proves only a range proof. Zk snarks, you can prove and verify any type of statement. The reason we chose still to create our zero-knowledge range proof is because if you have a specific zero-knowledge proof, it's much more efficient than a generic one, like a Zk snarks. And with efficient, I mean there's less calculational steps in order to verify it. To be specific, in Zcash, the Zk snarks, they require 10 times more calculations to verify than the zero-knowledge range proof. And that's particularly important in environments like Ethereum, where all the nodes in the network validate all the transactions. So it's in Ethereum, this is also represented by the gas cost. On the public network, you pay for your computational steps. But even if you run it in a private network, because everybody needs to validate all the transactions, it doesn't scale very well, so you need to be scarce with using the resources. Monero, it does not use Zk snarks, but it uses ring signatures, so you know that it's a valid signature from a group of signatures. Homomorphic encryption, additive homomorphic encryption to be specific, to validate that the sum of the inputs equals the sum of the outputs. And they do use a zero-knowledge range proof, similar to the one we built, and they use it to test that all the in and outputs are positive. You can't do a direct debit on Monero. You can do a withdrawal from that. So how does it relate to the platforms that we're using? First of all the platforms, they have pluggable consensus. But for Ethereum, they use proof of stake, or they're working on proof of stake to use in the future. They use proof of authority in the testnet. And currently it runs on a proof of work. For the privacy, you see that Corda uses confidential identities. Basically, you can use a different identity per transaction. You can choose to do so. The selective multicasting, so you only share transactions with those involved, but you do share the history from its issuance. And a separate notary cluster to prevent double spend. And they're looking at the integration of SGX. Hyperledger Fabric, it uses channels. And the best way to look at channels is like a WhatsApp group, or a Slack channel, or as you want to call it, where you have a restricted number of participants who can see the transactions, but those participants can see all the transactions in that channel. And so, for instance, if you have a trading platform, it's not so nice solution, because then you trade with different parties all the time. So, but if you have a static group which are allowed to see all the transactions between them, then you could consider using channels. Ethereum currently has no privacy solution, but they're working on the integration of CK snarks. And one of the issues there is that it takes so much computational steps or gas that you need to pay for the validations. And Quorum, the private transactions that I started with, which where you lose the consensus. But they're also looking at integration of SGX and the Zcash security layer. So you can do a Zcash payment and integrate that in the logic of Quorum. All right, that's it. Please remember to rate the session. I don't know if any questions came up already through the app or like that.
About the zero knowledge range.
Mm-hmm.
That you said that you will need a third party to validate these ranges. But isn't the whole blockchain principle based on peer-to-peer and not having the middleman?
Yeah, you need good question. Blockchain is indeed about decentralization and getting rid of a trusted third party. What you need the trust here for is not for the verification, because that's done by the whole network, but you need to have some starting point of a proof of your age. So if you look at, for instance, Bitcoin, the whole truth, everything that's on the ledger, also originates from the ledger. if I have a balance, then it's either because somebody paid me or because I got the mining report. But if you want to have a proof of your age, you can't ever have that on the blockchain unless you register every birth of a human being on the blockchain. But also that needs to be done by somebody who will not commit fraud. Then again, once you have that, you can use it decentralized. So if you want to use a decentralized application that does have an age requirement, say you want to do some gambling, or I think it's prediction market, the official name for which you need to be over 18, then indeed you have a signature and you need to trust that the government gave the right commitment on your age. But it's a fair point that the original thought of using blockchain is to have no trusted third party at all.
I'm very concerned about the Corda example that you gave. Maybe I didn't understand it very well, but it's about, well, the focus was here to, within a private network, that you don't want everybody to be able to see the transactions. And you say that you send the public key, or you basically, when you send a transaction, it's like it's validated across the whole network, and then the one person who has the private key, that they will be able to access it, and the other people will just see what or there's been some validation done by other team, but only picked up by the person who has the private key. But for me, what the confusing part is you also have a decentralized notaries, and like, to me, what I don't understand is then the person, it's like, it's difficult to keep all the transactions, keep track of everything in the notaries, because if I am not the person, the intended person who is supposed to be opening that transaction, then I don't know if my notaries will be looking as the same as the person next to me who does.
All right. So basically two questions. Let me first try to take away your concern with Corda. What you do in Corda, you have peer-to-peer communication. So say I do a payment, then the recipient of the payment will receive that, but he will also receive the history from the issuance, so he can verify that I'm indeed the owner. What he cannot verify is whether I already spent it. So he cannot verify the double spend. That's why there's the notary cluster, which is run by multiple parties, and they have a consensus algorithm to agree among them that this transaction that I'm about to do, whether that has been spent or not. So it's not that I use a different notary than somebody else, or the recipient, or because then indeed, if it would be disconnected functions, then they would allow double spend. But because they're connected and they have consensus, just like the Bitcoin network does, but not proof of work, but with PBFT or REPT, they do agree on whether something is a double spend or not. So they all know which are the transactions that have been spent.
But is it there for like it's just the algorithm and everybody just trusts it, and it's not there meant to be actually to be looked into? People don't actually look into the notaries, or?
What you typically want is that you, let's say you have a network of, say, 50 banks. That like some odd number, like 19 or 31 of them, run a notary cluster. They know which algorithm they use in order to reach consensus. And then because they run that, you can identify if one of those banks votes for invalid transactions. And you need a majority vote, so if it's only one, or actually the threshold is 1/3 of them, as long as 2/3 are honest, then 1/3 can try to cheat, but they can't, because you reach consensus in that group of notaries. Then you had a concern about private keys. I think that's related to the SGX. So no one knows these private keys apart from Intel. They're built in the machine, so nobody can access the encrypted transactions.
Well, they're in there, so couldn't you build something to read them?
Yes, and after the patch, no. So it's that's the part where it's ongoing research. So yeah, a fair point. It's that's a rat race between researchers and yeah.
Any other questions?
Thank you very much for your presentation. And I'm kind of newbie here in the blockchain technology, so maybe this question is quite stupid, so everyone knows already. But when we studied blockchain, we have one question which we cannot answer by ourselves, which is about what is the problem we need to use, or we have to use blockchain, or it is best fit. So for example, especially for private blockchain, we do not really find the reason why we have to use blockchain instead of Paxos or Raft. So that was the question we still cannot answer. Could you please give?
Yeah, it's a very good question actually. We had within the team we did quite some research on that, and basically the answer we came up with all the time is it's all about decentralization. When Paxos and Raft, they're not. They're crash failure tolerant consensus algorithms. So you need blockchain or with either proof of work or PBFT or whatever, if you want to run a decentralized solution. And then you should ask yourself, when do I want a decentralized solution? For instance, if you do payments between banks, it goes through a central system. If an ING customer does a payment to an ABN AMRO customer, then the payment goes through either a clearinghouse or it's settled at central bank, which introduces a cost, single point of failure, and reduced opening times. You can these transfers only work during opening hours, and I think in this region that works pretty well. But if you go from a small currency to another small currency, say Polish zloty to Mexican peso, then you go from the Polish zloty to typically a German bank where you're exchanging for euros. Then you go to another correspondent bank that makes them into dollars, and which has a connection with a Mexican bank that can credit the ultimate beneficiary his peso. Then you see that there's all these central systems per currency. which is why such a payment can take like 3 or 4 days. It can get lost somewhere along the road, and it's extremely expensive also. So basically the short answer is, whenever there's a problem with a centralized party, and whether that's just because it's inefficient or because it's censorship, or any other problem you might have with it, like for instance, there's a decentralized network, a decentralized social network, esteem it, because they don't want just one guy in Silicon Valley to determine what happens with your data and how much money he makes on it, etc. That's why there are many arguments to use decentralization. But the bottom line question, when should you use a blockchain or distributed ledger technology as opposed to traditional centralized technology? That is the centralization in this solution a problem?
Super. I think that's the time that we have for this session. Can we do a round of applause for Cees?
Thank you.